Impacts of drops on solids or liquids have been studied for more than 100 years and the pioneer work of Worthington. Nevertheless, many questions have been answered only recently. In which condition is the drop fragmented into satellites? In which conditions does it bounce completely off the surface? What is the maximum radius of spreading? What is the contact time? Here, we see a millimetric water drop impacting a superhydrophobic surface at a velocity of few meters per second. The drop is strongly deformed at impact due to the interchange of kinetic energy and surface energy, but it remains in one piece and bounces off the surface almost like an elastic ball. Next, we are going to discuss the time of contact of the drop with the solid, this time of contact being one of the key parameters for application which involve heat transfer between drops and solid surfaces, such as in a diesel engine. When a water drop impacts an hydrophobic surface, it bounces. The point I would like to discuss is how long is the contact. To discuss this, I first sketch the experiment. The drop has a radius r and an incoming velocity u0. It touches the surface at t equals 0. So this is when it first touches the solid surface. Then it deforms. And when the surface is superhydrophobic, it bounces back. And I call this time the contact time. What we know from the experiment is two things. The contact time is typically a few milliseconds when the drop velocity can vary from 1 to typically 5 meters per second. And in this case, what we observe is that the contact time does not depend on the impact velocity. And for a drop radius of typically 0.5 millimeter, this contact time is of the order of 3 milliseconds. This is the first experimental result. The second one is that the contact time depends on the drop radius that I put here in millimeters. And more precisely, the contact time increases with the drop radius. On a log-log plot, we observe a power 3/2. And the typical order of magnitude is for a drop radius of 1 millimeter, we have a contact time of 10 milliseconds. So these are the experimental results that we have on the contact time. So we have two results. First, the contact time does not depend on the velocity. And second, the contact time goes like the radius of the drop to the 3/2. These are the two ingredients that we will have to find in our model. To discuss the contact time, we are going to use an analogy. An analogy between the impacting drop that comes to the surface at the velocity u0 and an impacting spring that would have a stiffness K and a mass M, also coming towards the surface with the velocity u0. What we know from this experiment is that the spring will compress, and we call the compression X. In this case, the energy of the spring will go like kx squared once reaching the maximum compression, while here we expect the energy to go like gamma surface tension times the radius of the drop square. And so what we observe is that the two energies have the same structure where K is replaced, in the case of the drop, by surface tension. But in the case of the spring, we know exactly how it's going to happen, in the sense that the compression will be balanced by the initial kinetic energy, which allows us to evaluate the maximum compression that goes like the velocity times the square root of m divided by k, and thus an evaluation of the contact time that will go like x divided by u, which go simply like square root of m divided by k. And so if we use this analogy to get an expression of the contact time of our bouncing drop, we expect this bouncing contact time to go like m, so density times the radius cube, divided by k, which is here simply surface tension. So now let us have a look to this expression. First, the contact time does not depend on the velocity, which is correct as far as the experimental results are concerned. The second thing is that the contact time goes like the radius of the drop to the power 3/2, which is also coherent with what we have observed. The final comment is that if you use a numerical value for the density, 10 to the 3, r cube, which will be of the order of 10 to the minus 9 for a millimetric drop, and surface tension, which is of the order of 70, 10 to the minus 3, then you get a contact time of the order of 3 milliseconds, which is of the order that we have measured experimentally.
The contact time of bouncing drop can be markedly reduced by introducing macrotexture at the surface of a repellent material. A key point for understanding this effect is the way in which the texture reshapes the drop at impact. In this first movie, you can see that water, seen from the top, transiently adopts the shape of a butterfly when impacting a ridge. The ridge naturally tends to separate the drop into two parts, but it also prevents the liquid from spreading along its axis, which eventually leads to the formation of 4 lobes. If we assume that each of these blobs spreads and recoils independently, we understand that the contact time, a quantity sensitivity to the square root of the mass of liquid, will be divided by the square root of 4, that is 2. This way of thinking even allows us to understand the reduction of contact time on repellent dots. In this second movie, we observe that the water takes off with the shape of a ring, and defining the blobs as the subunits between the dot and the drop edges also leads to a reduction of contact time by a factor 2 as observed experimentally.
When the kinetic energy is sufficiently large, impact of drops on liquid surfaces leads to the fragmentation of interfaces and to the creation of new drops or bubbles. At an impact velocity of a few meters per second, a millimetric drop falling into a bath of the same liquid generates a column which pinches into ejected drops. If we examine the same phenomenon underneath the surface of water, we see that the cavity formed immediately after impact can pinch off to create a tiny air bubble. This bubble of sub-millimetric size rises then slowly to the surface. It turns out that the underwater sound associated to rain is directly correlated with the existence of this bubble and to its vibrations. Studying the noise in the ocean is a big topic for several applications, for mammal communication, for example, but also for submarine discretion. And so for a long time, people have put microphone in the ocean to listen to the noises. And what they have noticed is that this noise changes when it rains, and more particularly there is a clear peak at 10 kHz when the rain comes down and plunges into the oceans. And so what I would like to discuss in these few slides is the origin of this 10 kHz noise due to the rain. So to make a long story short, perhaps what we could start would be to look at the impact of a drop of rain of diameter d0 and initial velocity u0 impacting on the ocean. And the answer to the question would be to say, okay, once the impact is gone, we observe a small bubble. And the 10 kilohertz are associated to the vibration of this bubble, right? So this would be the final answer. In fact, what we are going to, let's say, to discuss is how is it that when you impact a water drop onto water, at the end you get a bubble, right? So this will be the question that we will try to address. If we want to be a little bit more quantitative about the possibility to observe this bubble, what can be done is to plot the region in which bubble are observed. So on the horizontal axis, I put the diameter d naught of the initial impacting drop, and this will be in millimeter. And on the vertical axis, I put the initial velocity of the drop, u naught, in meters per second. And then what appears on this plot is that there are several regions. So the bubble only appear above a first critical layer and below a second one. So this one, I will call it 1. This second boundary, I will call it 2. And there will be a final one there. And this one, I will call it 3. So the region which is enclosed, so this is the region where bubbles are observed. So they only appear, so if I put numbers, so here you have exactly 1 millimeter. You will observe those bubbles up to 4 millimeters drops. And the characteristic velocity are here 3 meters per second and there 4 meters per second. And so the bubbles are only entrapped below the ocean in this small region. And so our goal in the coming discussion is to understand why do we have to be above this first limit, why do we have to be below this second one, and how is it that the bubble are restrained in this small triangular shaped layer. So what we want to understand is the region where bubbles have been identified experimentally. So this region has 3 borders. First, brown one here, then a pink there, and the third white here. So what I'm going to do is to describe qualitatively the origin of these 3 boundaries, and then we will move to the scaling argument that allows us to understand why bubbles B can only exist in this region. So the sketch goes as follows. We take a raindrop of diameter d naught, velocity u naught, impacting on the ocean here. The first condition is that the energy of this drop has to be large enough in order to create a hole. So this will be the origin of the boundary number 1. Then what will happen is that the impact will create a cavity, and so this crater will have a subsequent dynamics, and the condition to produce the bubble is that wave will propagate from the edge of this crater towards the bottom part, and as they reach the bottom part, they're gonna isolate some part of the air, and this isolation is going to produce 2 things. First, a pinch off of the bubble, so this will be the final part of this event. So here we will identify the bubble, and then the remaining part of the jet will bounce off and produce a characteristic shape like this of upgoing jets and a subsequent bubble underneath that will vibrate. So the condition number 2 will be associated that the wave should have time to propagate to the bottom of the cavity before the closing of the cavity, right? So this will be the condition number 2 associated to the pink boundary. The last border that associates a relationship between U0 and D0, so border number 3, is related to the fact that in the rain, the drops of size D0, they fall at a velocity U0 in air. And so this means that the terminal velocity with which they will reach the ocean is associated to a balance between their weight and the friction with the air. And so this will give us the insight of these third boundaries. And so what we have to do in the next slides is to go, let's say, slowly to these 3 different stages in order to understand these 3 different boundaries. So the first condition we have to discuss is the possibility for the impacting drop to create a hole into the ocean. And so this will be, this condition will associate the initial kinetic energy of the drop, that goes like the density of the drop times the volume of the drop times the velocity square. And if this initial kinetic energy is larger than the surface energy, that will like this, then you expect a hole to be created. And so this condition tells you that you will only create a hole if U0 is larger than the square root of gamma divided by rho D0. And this is our first boundary. So in the plot that we have drawn, where we have U0 as a function of D0, we see here that as D0 increase, the velocity, the critical velocity decrease, and we have to be above this critical line. So we expect, in order to be able to create a hole into the ocean, to have to be above this boundary. So this was boundary number 1. So once we have created the hole in the ocean, the crater is going to expand up to a maximum size that I called big R here. This maximum size can be calculated as a balance between the initial kinetic energy of the drop and the final potential energy of the crater. And this final potential energy of the crater goes like rho g r to the 4th. This tells you that the maximum size of the crater will go like d0 cubed times u0 squared divided by g to the power 1/4. And from this evaluation of the size of the crater, you can deduce the time it will take for this crater to collapse due to the action of gravity. And so the time of collapse of the crater will go like square root of r divided by g, and you deduce from the above expression that this will scale like d0 to the cube, u0 to the square divided by g to the 5th to the power 1/8. So this will be the expression of the characteristic time of collapse of the crater that the raindrop has produced. What you want to trap a bubble is to propagate a wave along this crater before this collapsing time occurs. And so this is sketched like this. So what you want is to be able to propagate a wave from the edges to the final bottom part of the crater in order to entrap a bubble. So this is our criteria. And so in order to discuss the possibility of propagating the wave, we need to evaluate the time it takes for the wave to propagate over this cavity. And this time of propagation of the wave goes like the size of the crater divided by the characteristic velocity of the wave, which goes like square root of gamma divided by rho r. And so this gives you a characteristic time of propagation of the wave that goes like square root of rho times r cubed divided by gamma. In order to entrap the bubble, the characteristic time of propagation of the wave must be smaller than the characteristic time of collapse of the cavity that we have created. So if we impose the condition that this time has to be smaller than this one, this gives us a second condition on the critical velocity of the drop, and this critical velocity needed to entrap the bubble has to be smaller than gamma over rho divided by the square root of g times d naught to the cube. And this condition needed to entrap a bubble is at the origin of the second boundary that we had in our plot. And so what we have now after these two studies is two different boundary, one that goes like 1 over the square root of d naught and we have to be above. The second one that goes like 1 over the square root of d naught cube, so which is steeper. So this is the second boundary that we have just studied. And the velocity must be smaller than this boundary. So what we expect is, in order to fulfill the two conditions, there is only one small region where bubbles are going to be observed. And what we need to add to this analysis is now the fact that the rain produces drop of different d naught that falls in the air before reaching the ocean. And so this will allow us to discuss the third boundary. So the final point in our discussion on bubble entrapment is to observe that before reaching the ocean, the drop of rain moves in the air, and its velocity is going to be a function of its size. So this function results from a balance between its weight, so rho d naught cube g, and this weight is compensated by the friction in the air. And so the friction in the air goes like the density of the air times the velocity square of the drop times d naught to the square. And so this balance between the friction in the air and the weight of the drops gives you that the velocity of the drop at which it's going to reach the surface of the ocean will go like the square root of the density of the drop divided by the density of the air, which is of the order of 1,000, times gravity times the size of the drop. And so if you look for the order of magnitude of this velocity, you get that u naught goes like 10 to the 3 for the ratio of density, times 10 for gravity, times 10 to the minus 3 for a millimetric drop, square root, so this gives you square root of 10, and you end up to the conclusion that the velocity at which the drop will reach the ocean will be of the order of 3 meters per second. So now if we summarize what we have discussed so far in the diagram d naught and u naught, what we have seen is that in order to entrap the bubble, the velocity must be larger than this first limit, it must be lower than this second one. And what we just showed is that even if all the conditions in this region can produce bubble, there is a third one, a third condition that tells us that the velocity and the diameter are linked in the rain, which means that when we produce raindrops, we can only move along this third boundary. And so this means that in the rain, there will be only a small region here of diameter that will be able to entrap bubbles. And this small region is below two diameters, D1 and D2, which are very close to 1 millimeter. And so what we get from this diagram is that the only drops in a rain that can entrap the bubbles are around 1 millimeter. And the bubble that will entrap is of the order of a few hundreds of micron, and the vibration of this bubble produces the peak at 10 kilohertz. And so this is our final, let's say, explanation of the noise produced by the rain.
When a drop of water merges with a bath of water, the interface is strongly distorted so as to form a liquid finger, which pinches off, leading to a daughter drop. In turn, this drop goes through the same process, which produces a cascade of coalescence made of droplets smaller and smaller and quicker. The whole process lasts less than 1/10 of the second, invisible with the naked eye, but is an important cause of formation of aerosols when rain impacts the ocean.